Okay, sorry about that. Let's get started with the rest of chapter 5. The rest of chapter 5 is relatively easy. Okay. So I believe I ended about the glute transporter and how it works, bring things in. Okay. So the glute transporter, so you'll learn more about glute transporter when it comes to exercise and also diabetes and stuff. So let's talk more. So transporters are not magic, right? So they're proteins. So proteins can only work so quickly, okay? And so at some point, all your proteins are working all the time, and so you maximize out the production, okay? And you can't transport any more quickly than you are, okay? So one of the best examples of how what happens is diabetes. When you have diabetes, one of the symptoms of diabetes is you have sugar in your urine. Okay, and the way you kind of this works is when your blood has a lot level of sugar. Okay, your kidneys usually filter it out, and then it tries to reabsorb all the sugar back in because it wants to reabsorb it wants to keep the sugar. And usually when you're healthy, it does that very efficiently. Okay, but when you have diabetes, there's so much sugar in your bloodstream that your kidneys cannot reabsorb all the sugar. So some of the sugars, okay, end up in your urine still. Okay, so your sugar transporters, the kidneys saturate out, okay, and so you still end up with sugar in your urine. Okay. Okay. So galactose, if you have galactose, galactose and glucose are very similar. So they show the effects of competition as well. Okay. All right. Next thing is vesicular transport, and this one you guys probably pretty familiar with anatomy. So I'm just going to go over phagocytosis. I'm sure you guys can kind of understand phagocytosis on your own. Okay, but you got to understand the eating part of it. But then the next part of it is the digestion part of it. The digestion part, it uses the lysosomes. Okay, you have a phagosome, which is like the part of the cell that swallows the bacteria, and then it fuses with a lysosome. Lysosome has digestive enzymes, so now the pocket is called the phagolysosome, and eventually it digests away the bacteria. Okay. Okay. So endocytosis not only swallows bacteria, that's the classic example, but that's not the only thing it does. Okay. It also has small little vesicles that it swallows called penocytosis. Penocytosis, peno means small. So penocytosis is small sipping or sipping as opposed to eating. And it pulls in little samples of the extracellular fluid, and that tells the cell exactly what's outside. And then the receptor mediated endocytosis is receptor mediated, which means something has to bind to the receptor, and that receptor will force that part of the cell to invaginate itself. And if you have enough receptors responding, that those things will invaginate into a circle, and you will cause it to be taken inside. Okay. Okay, exocytosis. Okay, so here's exocytosis. Exocytosis is basically the exact opposite of endocytosis. Okay. So this is sorry. So exocytosis. You go. This is endo, and this is exo. So exocytosis. Okay. You exit the cell the same way using snares. Okay. That facilitate the vesicle. So the purpose of the snare is really to facilitate the docking of the bubble into the membrane, and then the membrane opens out to the outside. Okay, so the transporting epithelia are polarized. Okay, so if you want to transport something from one side to the other, there's one side and the other. So these two sides cannot be the same. Okay, so one's input, one is output, right? So you need these two sides to be very different. The input side will have usually microvilli. Microvilli increases the surface area, so it increases the absorption much faster. Okay. All right. The dumping out of the thing is called secretion. So getting it transport from the lumen to the ECF is by definition absorption. Going from the ECF out is by definition secretion. Okay. Okay. So this is an example: transepithelial absorption of glucose. Okay. Okay. So before I explain this, one, you want all the glucose you can possibly get your hands on. Okay, in the lumen of the kidney or intestines, you do not want to lose glucose, right? You're eating sugar, you don't want to poop it back out or pee it out. You want desperately to try to get it into your bloodstream. Okay, so you want to keep all the glucose you want. So even if there's low concentrations of glucose, you still want it. Okay, all right. So first thing you do, actually, I want you to pay attention right here. Okay, this is the sodium potassium pump. Remember, I'm going to pump all the sodium out of the cell. Okay, so I'm going to pump all the sodium out of the cell. So now any sodium I want that's outside is going to want to come rushing in. Okay, so the sodium that comes in, but it goes through a channel that also allows glucose to come in along with it. So now I have sodium coming in along with the glucose. So glucose sodium co-transport. Okay, now that sodium, as soon as it comes in, I'm gonna push it back out. Okay, the glucose that comes in, I'm gonna push it back out. So I'm gonna try to keep this flowing. Okay, hopefully that makes sense, you guys. Pause recording. Okay, so we went. You can skip the paracellular transport. So I just explained the uphill downhill side. Okay, so the uphill side is this one where I'm using ATP to set up this gradient, and then this side is the downhill side. You're going from high to low. Okay. Okay. So This one you can see the transcytosis across the capillary epithelium. This is just really short pathways. All right, the resting membrane potential. This sets up the next couple of chapters. So let me go over this in slightly more detail than usual. Okay, so your body is electrically neutral. Okay, so you have a positive charge somewhere, you have a negative charge somewhere else to balance it. Okay, but there is a chemical disequilibrium between the ICF and the ECF. The ICF, the inside of the cell, is negatively charged. The outside of the cell is positively charged. Okay, the only way this works is the phospholipid bilayer doesn't usually allow charge to come through very easily. So you can set up a negative charge on one side and a positive charge on the other. So the inside of the cell is negatively charged, the outside of the cell is positively charged. Okay, the way we think about it, really, so we kind of set the outside to 0, and so the inside of the cell has a negative charge, a much bigger negative charge. Okay, because we can just, instead of being 35, negative 35 on the outside and plus 35 on the inside, we think of the outside being 0 and the inside being negative 7. Okay, so here you go. This is the membrane potential. Okay, so there's positive charges on the outside, negative charges on the inside. Okay. All right. So here, okay, this is okay. So this is the normal cell, the default cell. Remember, right now there's no membrane potential. Okay, this is what happens when you are dead. Okay, okay. So everything is the same inside outside. So electrically neutral, blah blah. So the system is in chemical equilibrium. Okay, so we're going to put in a leak for potassium. Potassium, it can actually cross the potassium. Potassium can actually cross relatively easily. Okay. Okay, so potassium will leak out of the cell. Okay. Okay. That way, as it leaks out, now the outside is positive and the inside is negative. Okay. Okay. So, but as it leaks out, okay, remember the sodium, sorry, not sodium, the potassium wants to leak out because there's no potassium on the outside, so it wants to leak out. But as it comes out, okay, it is a positive charge coming out, which leaves the negative charges on the inside, which means now you have a positive charge on the outside and a negative charge on the inside, which means the positive and negative charges attract each other. Okay, so we now have two separate things to account for. One is the chemical gradient, and one is the electrical gradient. Okay, now we want to balance basically the two gradients together. Okay, the concentration gradient sending up K plus out is exactly opposed by the electrical group gradient pulling the K plus in. Okay, so you can see these two arrows are equal in length. Okay, so just as much sodium as, or I keep saying sodium, just as much potassium is coming out as coming back in. Okay. Okay. So this is the membrane potential. Okay, you don't have to worry about the Nernst equation, but you do have to know what these are. So the two biggest ones really are the sodium and potassium channels, okay, causing the difference in equilibrium potential. Okay, all right, so here, okay, you can set this as 0, and you can see where the intercellular fluid is. Okay. All right. Okay, so you can see this the same way. So the membrane potential is -70, okay, which means the cell is -70 millivolts. Okay, so more terminology. Hyperpolarization. So that means it's polar, right? Polar means the two sides are not equal to each other. So if I want to make it more polar, more different, I am hyperpolarizing. If I want to make it less different, closer to 0, I'm depolarizing. Okay. Okay. So let me share screen. Make sure you can hear everything.
In this video, we will look at how cells develop the electrical disequilibrium known as the resting membrane potential difference, or membrane potential for short. The system we will use for this demonstration consists of two compartments separated by a semi-permeable membrane that does not allow ions to cross. In compartment A, we place a solution of sodium chloride ions. In compartment B, we place an equal concentration of potassium and protein anions. Following the law of electrical neutrality, for every positive ion there is a negative ion, so the net charge on each side of the membrane is 0. There is a concentration gradient present for each of the 4 ion species, with sodium and chloride concentrated in A, potassium and protein anions concentrated in B. However, the membrane separating the compartments doesn't allow ions to move, so nothing is going to happen. Now we can add a channel that allows only potassium to cross the membrane. Predict what you think will happen to the ions in each compartment as soon as we allow potassium to move. As soon as we make the membrane permeable to potassium, potassium will move down its concentration gradient into compartment A. If the only factor influencing potassium movement was the concentration gradient, potassium would continue to move into compartment A until the concentration in A equaled the concentration in B. But we must also consider the electrical gradient created by the movement of an ion across the membrane. As soon as positively charged potassium entered compartment A, an electrical potential difference was created. Compartment A now has a net charge of +1, and compartment B, with an unmatched protein anion, has a net charge of -1. At this point, there are two forces acting on potassium. The concentration gradient favors movement of potassium from compartment B into compartment A. But compartment A now has a positive electrical charge, and like charges repel each other. So that means that the electrical gradient favors the movement of K plus from A back into B. At some point, movement down the concentration gradient will be exactly opposed by movement on the electrical gradient, and the system will come to equilibrium, where movement from B to A is equal to movement from A to B. The electrical gradient that exactly opposes a given concentration gradient for an ion is called the equilibrium potential for the ion. In living cells, the equilibrium potential for any ion can be calculated using the Nernst equation.
Okay, so sorry, clearly for you that video will not be available in your PDF because I tried to save everything as a PowerPoint, but it's too big for Canvas, so everything's in PDF. So hopefully you can watch that if you want to. I believe this is also available on your Master in AAP course, so you can play that all you want. All right. So, okay. So that's the resting membrane potential of the cell. The resting membrane potential is mostly, but not completely, not controlled by the sodium potassium pump. Okay. So sodium is constantly leaking in, or sodium is constantly leaking in a little bit. Potassium is constantly leaking out about a little bit. So we spend a lot of energy actually maintaining this gradient. Okay. Okay. You'll see what happens next chapter when we talk about depolarization, repolarization, and hyperpolarization. Okay. All right. So let's give a really cool example. Okay, glucose. Okay. Okay. So you guys are probably educated enough and old enough to realize what glucose does and what insulin does. So so glucose goes up in the bloodstream, your body secretes insulin. Okay, so now here are the steps to how. Okay. Okay, so glucose is low in the blood. Okay, this is the beta cell at rest. Okay, everything is normal. There's low glucose in the bloodstream. You haven't eaten for a while, so there's low glucose. So there's very little things that glute transport can do. So there's no glucose entering the beta, or very little glucose entering the beta cell. There always is a little bit, okay, but not a lot. Okay, so glucose leaks in a little bit. There's very low metabolism. There's very low ATP. Okay, the very low ATP doesn't do anything. So the potassium channels, the sodium channels open. Okay, so no insulin is released. Blah. Okay, so if there's low ATP, potassium can get out. Okay, now let's look what happens when you do eat glucose. When you do eat glucose, all of a sudden more glucose can come in, therefore you have more ATP. ATP will bind to this channel and close the channel. If you close the channel, okay, the potassium cannot get out. If the potassium cannot get out, okay, the cell depolarizes. Okay, so more and more. Remember that the inside of the cell is negatively charged. If the sodium or potassium can't get out, it stays in, so it becomes more and more positively charged. So it depolarizes. Okay, when it depolarizes, okay, the membrane potential gets less, and that actually triggers the calcium channel opening. The calcium channel opens and calcium comes flooding into the beta cell. The calcium one of the things about calcium is it works as an intercellular messenger. The intercellular messenger component of calcium will actually bind to these vesicles and cause them to release. And that will release the insulin. So high glucose leads indirectly to insulin release. Okay. All right. Hopefully that makes sense to you guys. Stop sharing.